Well, the next paper is, I guess, partially out of context. It really should have gone in this morning's session. It's by Dr. Johnson on the energization of ionospheric particles.
I thought what I'd do this afternoon, in view of the shortness of the time, is to review just briefly the status on the O+ observations that we have made, and then to present some more recent results on the observations of helium, energetic helium plus ions, and then finally to comment on the significance of both of these, at least as I see it. The first slide is just an example of some energy spectra taken during the December 17th, 1971 magnetic storm with an energetic ion mass spectrometer that covers the energy range from 0.7 of a kilovolt to 12 kilovolts. This was a velocity filter in front of an electrostatic analyzer, which provides one a measurement of the mass per unit charge at a given energy. So we have a mass spectrum at each of 9 energy points over this energy range. The reason for showing this is that it's an indication of the range of characteristics, spectral characteristics. At times the fluxes are indeed very soft. The intensities can be fairly high. This is a differential number flux. This is an intermediate case which seems to have a low tail as well as a harder component, and then one which has essentially only a hard component.
Could you show the energy scale?
Could you raise the slide up slightly? Well, this point's 0.7 of a kilovolt, and this point is 12 kilovolts. The next slide shows an example. He has to hand feed these because they're too thick, apparently. This is an example of some intensities for protons and ions during the same storm in December 17th. This is a number of passes in the northern and southern hemisphere taken during that storm. The L value here is from 2 to over 15. The magnetic latitude is shown here. This is integrated over the spectrum, over our spectral measurements from 0.7 to 12 kilovolts. The purpose here is to show that in this energy range, the ion intensity is often comparable and sometimes larger than the proton intensity that's precipitating into the atmosphere. I should emphasize that these are observations made on a polar orbiting satellite at 800 kilometers, and the instrument is looking at 55 degrees to the zenith, so it's sampling precipitated particles. After looking at this one storm, the question comes up as to what is the local time characteristic of these fluxes? Are they there in all magnetic storms? We, from a very quick survey, concluded that they were primarily storm associated. We looked at 12 storms during the period from December 1971 until mid-December 1972. We looked at them in a synoptic sense, that is, we took 3 passes of data in each of the storm, spread out over the storm time. The next slide will show a summary of that data, plotted as a function of magnetic latitude, 80, 70, 60, 50, and local magnetic time, noon being down here and this midnight. The lines themselves indicate the region over which we observed the energetic oxygen ions above the background of the instrument, about 10 to the 5th ions per square centimeter per second per steradian. The dot indicates the position of the peak intensity of the flux. Now from this slide, one can see 2 things rather clearly. One is that these energetic oxygen ions are precipitating at all local times, albeit over a number of storms, because on the low altitude satellite we are precessing only 2/3 of a degree per day, so it takes about 9 months to precess fully around to get a full local time sampling. The other thing is that the region over which it's precipitating is also very large. we see orientation with respect to essentially the trapping boundary or the lower edge of the auroral oval, for example. I don't have time to show other data to show that in more detail. Now, a point I'd like to make here is that the very wide local time spread, the very wide latitudinal spread, to me would seem to make it very difficult to explain these ions as essentially originating from a source, and we're seeing them immediately after being injected and accelerated. The reason for that is that the ionospheric characteristics vary widely in latitude, in local time and in latitude, and the magnetospheric characteristics also vary widely in latitude and local time. Therefore, to have just the right conditions to inject and precipitate the fluxes over this wide region seems unlikely. Therefore, I conclude that there's probably a large amount of transport going on, and therefore, even though we're looking only at the precipitated component, there probably is also a sizable trap component that is taking part in the transport. Now I'd like to switch to the helium plus data. First, I'd like to comment that whereas we see the energetic oxygen ions essentially during every magnetic storm, there are no magnetic storms that we've looked at that we have not seen it. The intensity of the oxygen ions is often comparable to the protons. In contrast to this, it's taken a great deal of searching to find energetic helium plus ions. This may be related to the ionospheric characteristics in the source region, or perhaps the energization process itself. The first example, or the first slide in this area, will show a mass spectrum. Just to indicate, oh, I'm sorry, let me back up. This is the peak intensities from the previous plot of the oxygen ions. There was a black dot indicating the position of the peak intensities. This is the magnitude of that peak, plotted as a function of magnetic time. The only significant point here, I think, there does seem to be some local time dependence. The more significant point is that the fluxes are indeed quite large. The dotted line would be 1/10 of an erg per square centimeter per second precipitating if the fluxes were isotropic. And we took an average of 5 kilovolts for the energy of the ions. The helium plus spectrum. Could you turn that the other way, please?
Turn it back the other way?
No, I'm sorry. Turn it by 90 degrees.
Sure.
So that. Yeah. Oh, very good. Thank you. This is the mass spectrum for 3 different energy channels. The mass per unit charge is along this axis. Protons being here, this would be the position of alpha particles, this helium plus and this O plus. Just want to indicate that although we had to average this over several sweeps of the instrument, the mass peak is well defined, and the definition of it as helium plus is quite conclusive. The next slide will show the spectra taken during this time. Again, it is sideways, but let's not take time to change that. I'll let you tip your head to the left. This is the energy scale along here, and there are 3 plots here. This is the hydrogen. This is the differential number flux along here. This is the helium plus block in the 1 to 5 kilovolt range. And this is the O plus from 1 to 12 kilovolt range. The only thing I wanted to indicate here is that there's a very soft proton spectrum and a very soft helium plus spectrum observed. These are in contrast to a rather hard, relatively hard O plus spectrum. This is the latitudinal distribution now of the fluxes that were observed. Along the bottom being the the L values starting at 4.4 to 12.5. This being the intensity of the flux integrated over the spectrum. This is hydrogen at the top, helium in the middle, and oxygen at the bottom. The main feature I want to indicate here is that these fluxes are all co-located, perhaps indicating that they might have come from the same source. At least that's the inference. I should indicate that this occurred at a local magnetic time of 0700, and K sub p in this case was around 5. We only have really 3 cases of the helium plus data. This is out of surveying perhaps 150 orbits. So it's a relatively infrequent event. The peak intensity there was about 0.03 ergs per square centimeter per second per steradian. Now I'd like to return, this is sort of a synoptic picture. Now I'd like to return to the O plus to show the location of the O plus ions in cases when the latitudinal distribution of the ions are somewhat confined. That is to say, instead of looking relative to the electron fluxes and proton fluxes for cases where the ions are spread all over, indicating perhaps a large amount of transport, I just want to indicate by this example some general characteristics relative to the plasma sheet electrons. What's plotted here along the bottom is the latitude from 68 down to 56 degrees at this point. And these are the responses, essentially logarithmic, of the electron detectors in the energy ranges indicated, from 60 volts to 3/10 up to the highest differential contiguous channel going from 11 to 40 kilovolts. Then there is 2 detectors on here. These are more energetic electrons from 130 kilovolts to 1 MeV, but measured at 2 angles, one at 15 degrees, that is the precipitated component, and the other one at 90 degrees, looking at the trap component. This is the oxygen ion along here, indicating a precipitation region at this point, and this is the protons in the same energy range from 7/10 to 12 kilovolts. The main thing I'd like to note here is that the ions do seem to be, when they are not spread all over, inside the trapping boundary. They also seem to be fairly well correlated with the very soft inner edge of what we would consider here to be the plasma sheet electrons. This was a local time of about 2030. I think at that point I'll stop. Thank you.
I have a question. What's the flux? Okay. What are the flux values for your 130 keV to 1 MeV electrons, the precipitating component?
Oh, in here, I'm sorry, I don't know those offhand. That's just a count rate scale, so I don't know those. I could dig those up for you if you'd like.
Could I have a quick clarification? I understood you to say that helium was less prevalent. Is it more intense in the flux, however, when you do see it? It seemed so from your diagram.
Well, more intense than the protons?
No, than the oxygen.
No. On the example that I showed, it was more intense, but that's not typical. The oxygen flux typically dominates. That is, its order, another order of magnitude higher at the peak intensity.
That was just an exception.
Yes, right.
Dick? Right, I've got it. Since you see these precipitating in conjunction with some protons, are you willing or unwilling to associate these ions with the positive ion component of the plasma sheet?
Well, I really have no way, are you inferring that they might be carried in with the plasma sheet? Well, I have no way of knowing that. Perhaps the thing to note there is that they are not distributed throughout the plasma sheet electrons, but only on the very inner or low equatorial side of the plasma sheet, right where the electron fluxes become very soft.
But you would expect the positive ion portion of that plasma sheet to extend somewhat equatorward of the electron portion of it. So these might be indeed part of the positive ion plasma sheet.
That's right. They would be a component in that, yes. Ted?
Whalen has looked in Aurora for helium, and he's found it, although he's found double plus. Have you seen any double plus helium, or can you distinguish that?
Oh yes, we can distinguish that, and we've seen many cases of helium double plus. However, primarily on the day side in the polar cusp region. We have seen some cases in the midnight sector, or in, I should say, the cases we saw were really in the morning sector, I guess.
Now, the one example you showed of helium singly ionized, that was at about an L of 7.6 or so, I judged from that. Would you associate that then with the auroral oval? It was very narrow.
There's really not enough statistics to say.
Well, of your 3 or 4 cases, do they all occur at that L value with that narrow distribution in latitude?
Let's see, Dick. The OB-118 case was also high, and the other was about the same place. I'd say yes.
Since O plus is available in the ionosphere at all local times, I don't quite understand how you distinguish between transport, which you say is happening, and a source mechanism that's prevalent at all local times.
Well, I only infer that with a very large hand wave, in the sense that the mechanism that might energize the oxygen ions are presumably related to the ionospheric characteristics and to the magnetospheric characteristics further out. Both of these change rapidly with latitude, and we see the ions from as deep in as L equal 2 as far out as L equal 12. And therefore, it seems unlikely that the plasma conditions would be just right to have that source operating over that wide range.